with Vlasov-Maxwell equations.
Thank you very much. Can you hear me? Yes. 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 So thank you very much for the invitation. It has been a long time since I was not speaking to a live audience, so it's a real pleasure to speak to real people. And so I will present essentially a work in progress that we do in the group of Eric Sonnenbrücker, who will be giving the talk following mine at the Max Planck Institute in Garching, close to Munich. And the main objective here is to set a good framework, a good setting for efficient particle methods, and to implement them in large codes. So I will not be speaking about the implementation and the codes, but this is an important aspect of the objective. And so it's very convenient that my talk is following the one of Antoine, because I will also address some of the issues that he mentioned in this talk. And so I'm very happy that some of these issues have been described already. So so it's a joint work. So most of what I will be presenting has been joint work with Jacob Ameres, who was a PhD student of Eric, Katharina Korman, who is now in Bochum, and Eric, who is in Garching, and some more recent developments on the finite element side have been done in collaboration with Yaman Güçlü and Said Hadjout. Okay. Okay, so let's start with an introduction and present the main results. So in this talk, I will be considering the Vlasov-Maxwell system. So I recall the general form of the Vlasov equation, where you transport this plasma density function F, and the Maxwell equations, where you evolve the electromagnetic field E and B. And here you have a transport structure for the Vlasov equation. The value of this phase space density is constant along the trajectories, capital X, capital V. And in the Maxwell equations, you have also a structure, namely a Rham structure between the two fields, and that also involves relations with the potentials, the electrostatic potential phi, and the vector potential A. Here, the coupling terms are a key element in the system. The coupling term in the Vlasov equation is the Lorentz force, okay, which involves the electric field and the magnetic field here. And in the Maxwell equations, the coupling term is the current density, which is the first moment, the first velocity moment of the plasma density. And here we consider as a general discretization ansatz a particle discretization for the Vlasov equation. Well, essentially for all the reasons that Antoine mentioned, and because a very important aspect of the Vlasov equation is that it is a transport equation. So it's very natural to use particles to discretize F, and plus all the good reasons that Antoine mentioned. And for the Maxwell equations, we will consider finite element discretizations, but I should add in a very large sense, and I will come back to that. And one of the main reasons why we consider finite element discretizations for the Maxwell equations is because it has been studied for several decades now, that they can preserve at the discrete level this Rham structure that I will describe in the next slides. So the main loop of particle or particle in cell schemes is the following. On the top, I recall the main elements of the particle discretization of the Vlasov equation. Okay, so the numerical unknowns are the positions and velocities of the particles and the weights. And you push the particles by following the trajectories. And here you have this coupling term, the Lorentz force, that is applied to the velocity. And on the Maxwell side, you have a finite element discretization, which here I denote by two spaces, two discrete spaces. One space where you can, for instance, take the magnetic field, the discrete magnetic field, say in V1, and the electric field, you can take it in V2. There are different choices. Here I take this one as an example. And the curl, the idea is that if you take the curl of a field in this first space, then you end up in the second space, which allows you to write this relation in the space of E, for instance. Okay. And you will have another relation, another discrete relation for the Faraday equation, where this curl operator will have in general to be discrete. You cannot take the true curl of a field here and go back to this space. And you can take the true curl in this direction, but you will have to take a discrete curl to go in the other direction. Okay, so there are two different curl operators. And you already see that here the second coupling term, so the first coupling term was the Lorentz force, and the second coupling term, the current density, needs to be also approximated, discretized in a finite element space. So again, here finite element is is meant in a very general way. It could be a Fourier space, polynomial finite elements, spline finite elements, generalized finite differences. Okay, so I will specify in which sense I say finite elements. Okay. So the main question behind the whole talk is how to compute, how to define and compute these coupling terms, the Lorentz force and the current deposition, in such a way that the whole discretization of the nonlinear system preserves key stability properties. Okay, so Antoine's talk was more about accuracy questions, noise issues. I will only focus on long time stability issues. And here the main idea is that if you have, I mean, there are a lot of good methods for the long time stable approximation of a transport equation, and the whole structure preserving finite element theory of Maxwell equations give you quite easily a lot of stability for the solutions of the Maxwell equations. So the difficult part is to couple the two different discretizations together in order to have this long time stability for the full nonlinear system. And I should stress that the two discretization ansatz are completely different. Okay, the particles they are completely unstructured. Okay, the positions and velocities can be completely arbitrary here, and these discrete fields they need to belong to these finite dimensional spaces. Okay. And when I say long time stability, I have in particular in mind the Hamiltonian structure of the Vlasov-Maxwell system. So at the continuous level, the exact solutions, F, E, and B, they satisfy an action principle. They are the extremas of the action functional, which is this time integral of the Lagrangian functional for particular generalized trajectories and generalized solutions. And the Lagrangian functional, you can take this one. given by law in 58. And you see that it involves different terms for the Maxwell equations, for the transport Vlasov equation, and some coupling terms. In particular, the coupling terms are here. You see that you have essentially the velocity multiplying the vector potential in the Lagrangian, and here the charge density multiplying the electrostatic potential. And with this Lagrangian functional, then you can show that the extrema of the action satisfy the Vlasov-Maxwell system. A consequence of, of that is a Hamiltonian structure. The solutions can be expressed, the system can be expressed as Hamiltonian equations with a Hamiltonian functional, which is the standard energy for the plasma and the field, and a bracket here, a skew-symmetric bracket, which has this form. This one was proposed by Morrison, Marder, and Weinstein in the early 80s. And it is a Poisson bracket. It satisfies the Jacobi identity. And you have here Casimirs, which are invariants of the system. And this Hamiltonian structure is a key for a lot of physics invariants and a lot of stability for the system. And we would like to preserve those kind of structures at the discrete level for the sake of long-time stability. So the main result is the following. We can construct general particle field discretizations. So I should specify semi-discretizations. Okay, here the discretizations that I'm describing are essentially in space. Particles are discretizing in space, the Vlasov equation, and this generalized finite element is a space discretization of the Maxwell equations. Then the time discretization is also an important issue, but I will focus on the space discretization here. So we are able to describe particle finite element field discretizations that is variational, that follows an action principle, and where the whole coupling is described by this commuting the Rham diagram, which is well known in the analysis of structure-preserving finite elements. I quote a few works that have been done since the 70s and up to the last decade, where a very important unifying analysis has been done by the Arnold Falk-Winter group. Okay, so this the Rham diagram and commuting diagram, what you have here is you have essentially two rows of functional spaces. The first row essentially describes infinite dimensional, so the exact, the continuous infinite dimensional fields and sources. So okay, and on the bottom row, you have the finite element fields, so the discrete spaces, sorry, so the discrete spaces that can be either Fourier spaces or truncated Fourier spaces, or finite element, standard finite element spaces on triangles or quadrangles, something like that. And here you have the de Rham sequences between the spaces with the grad, curl, and divergence operators. And I also denote the adjoint differential operators that go in the other direction with a small h to remind that in general they are discrete operators. And these arrows that go to from the continuous spaces to the discrete ones, they are projection operators. Actually, they don't need to be projection operators. They could be in general approximation operators. And their fundamental property is that they commute with the differential operators, in the sense that here, for instance, if you take, so here I highlighted these two operators, P2 and P3, because they will be involved, with this example, they will be involved with the particle field coupling. So you can see here what I wrote is that in this line, on this row, you can see the exact fields, the exact solutions of the Maxwell equation, but actually you can also see the fields and current densities discretized by particles. Okay, they also belong in some sense to these spaces because they do not belong to the discrete spaces, so they belong to larger spaces. And when you want to compute, for instance, here the current density, which was a little bit above, so here, okay, this current density, for instance, then you will want to project in a discrete space, for instance, in V2, the continuous current density that you can compute from the particles. Okay, maybe with some smoothing or not. And the projection, the discretization operator that you will use to compute this discrete current density in the finite element spaces, let's call it P2. And the commuting projection means that if you project, say, a current density with P2 and you take the divergence, then you should find exactly the same thing as if you had taken the divergence of the current density and then projected with a second projection operator called P3. Okay. So of course, if you consider the divergence of the current density, then it means that you are thinking about the Gauss law. So these two projection operators, they will be naturally associated with the preservation of the Gauss law. But actually, what is so this was already known for a few years. But the new result is that this setting, the existence of a sequence of discrete spaces with projection or approximation operators that commute with these differential operators, this very general setting is enough to write a fully coupled particle field scheme that satisfies an action principle and has a Hamiltonian structure. An interesting point is that the resulting scheme is gauge-free. You can express it completely in terms of the discrete electric and magnetic fields expressed in terms of the discrete differential operators applied to these potentials. Okay, the discrete Lagrangian will be expressed, will be a function of the electromagnetic potentials, but the resulting scheme is not. It is only expressed in terms of E and B, just as at the continuous level, the Hamiltonian formulation can be expressed only with the electromagnetic field, and you don't need to involve the potentials. And it's a very flexible framework because it's very easy to compute, to define these projection operators that commute with the Rham sequences. And so I will describe a few examples. One is a class of Gempic schemes. So the Gempic scheme was the name given to this kind of schemes for a particular choice of finite elements. So they were using spline finite elements, point particles, and a strong Faraday ansatz, which means essentially that the electric field was here and the magnetic field was in this div conforming space. But actually, other choices are possible. And we can rewrite this kind of schemes for general finite element and also broken finite elements, DG spaces. And we can also apply these constructions to Fourier spaces to have spectral solvers. And then an interesting aspect of this framework is that you have actually two degrees of freedom in the construction in this framework. You have more, but two important degrees of freedom. The one is the construction of the discrete spaces. Okay, so you can take finite element or DG spaces here or Fourier spaces. And the second one is once you have chosen the discrete spaces, you can choose different kind of projection operators, and this will essentially influence the coupling, the particle field coupling technique. And in the scope of Fourier spaces, if you take different projection operators here, you can obtain the so-called particle in Fourier coupling that Antoine also mentioned, which is essentially a gridless projection. There is no grid at any place in the solver. The fields are solved in Fourier spaces, and the coupling is done without a grid. And another type of coupling where you essentially replace the gridless projection with DFT projections. So you essentially compute the Fourier modes with a DFT. And it's possible to do that within this Hamiltonian framework. I should also mention, because it was something that Antoine talked a lot about, that filtering, smoothing and filtering is naturally allowed in this framework. So you see, if you have a current density here or a charge density that is here, and you want to discretize it, you may use a projection operator, which in the sense that if your charge density was exactly already in the discrete space, then you don't change it. But it's not very likely to be the case, but okay. But you can also want to filter it, to smooth it. And if you smooth it, it will not be a projection. Okay, you will modify the source. So it will not be a projection. So usually these diagrams are expressed in terms of commuting projections. And the main reason for that is that the stability properties, let's say the general stability properties of the finite element solvers that involve discrete the Rham diagrams are analyzed through the existence of projection operators which are commuting and which are stable either in L2 or in the natural Hilbert spaces that you would have here. So H1, H curl, H div, and L2. And for that, the projection operators will be projections. Okay, so the operators in this diagram for the theoretical stability analysis of these spaces, the IMSUP conditions between these spaces and so on, they are analyzed through essentially L2 stable commuting projections. Here the diagram is so if you are familiar with this kind of analysis or literature, the diagram, I stress that the diagram here is different in the sense that these operators, they don't need to be L2 stable. They don't need to be projection operators. They just need to commute. Okay. And the main reason that here is that we are not really analyzing the stability properties of these spaces. We assume that they have been analyzed elsewhere, but we want to actually implement. We want to actually compute the effect of these projections on particle sources. Okay, so we don't need to be L2 stable, and we don't need to be projections. We can just be approximations, and filtering is okay, smoothing is okay. Okay. Very good. So now that the introduction is over, I can describe a little bit, quickly go through the slides. Okay, so one first example of applications is finite elements on curvilinear domains and maybe multiple patches, where each patch has its own mapping. And so you have this omega k's are the patches, and you can compute, you can build a Rham diagram like that for the global spaces. So I will skip the details. The construction is to start on the reference patch, which is a tensor product Cartesian domain, and you build tensor product spaces here, and the degrees of freedom, they are geometric. You evaluate for the first space V0, you evaluate the point values. Here you evaluate the integrals on the small edges between the it's the same grid, So here you look at the nodes, here the small edges, and here in the y direction. And for the last space, here it's in V2, you have 3 spaces. You evaluate the integral on the faces, here on each face. And in 3D, you would have a last set of degrees of freedom where you have evaluations, integrals on small cells. And when you construct these the spaces and the degrees of freedom on the mapped patches, you involve these push-forward operators. You have one push-forward operator for every position in the sequence, which you can see as proxy fields for differential forms. And so you have these push-forward operators, and you construct the spaces by pushing forward the reference fields. These push-forward operators, they commute with the differential operators so that you have the Rham sequences on every mapped patch, and you define the degrees of freedom by pulling back the fields and evaluating the geometric degrees of freedom. And by doing that, you have exactly the same kind of geometric degrees of freedom on the mapped patches for all the edges and faces and cells that have been mapped forward. You have local basis functions with this procedure. And the finite element projections that you define like that, by interpolating this, they will satisfy a commuting diagram property because of geometrical relations. Okay, so the geometrical relations here are shown, for instance, for the curl operator. If you look at this part of the diagram here with the P1 and P2 projections, then essentially you note that P1 and P2, they are characterized by the fact that they interpolate the degrees of freedom of a function. So here you see that as a source, and you project the source. Projecting the source means that you are interpolating the degrees of freedom. So you can compute the degrees of freedom in V2 of the curl of your function. Those are the fluxes of the curl. The fluxes of the curl are the circulations of the function along on the boundary of a face. And this is exactly a linear combination of the one type degrees of freedom of U. And theCij's, they correspond exactly to the orientation. It's -1, 0, or +1. So it's the orientation of the edge EJ in the face Fi that was here. This shows two things. If you apply that to the projection of the curl, then you end up with this linear combination, and you obtain exactly the same thing if you apply that to the curl of a projected solution, of a projected function. So it means that the two are equal. So you have proven that the diagram was commuting. It also shows that the operator matrix of the curl in these bases, in these geometrical bases, is mapping independent, because it's only the graph incidence matrix in your edges, faces, and nodes. And you have, of course, similar relations for the gradient and the divergence. So you can construct these projection operators with these geometrical interpolation degrees of freedom. And you can also see that if you define the projection with a smoothing, so it will not be a projection anymore, by interpolating not the degrees of freedom of U, but the degrees of freedom of a convolution of U, because the convolution will commute with the curl, then you will still have the same commuting property for the smoothed projection. Okay, so smoothing is absolutely not a problem in this setting. Second example with spectral particle schemes. So I recall the Maxwell equations in Fourier space and the particle equations. And so here the sources, the coupling terms are these the Fourier modes of the current density and the pushing field that the particles will see and that you have to compute. And this is the unknown again. And you have two flavors of these spectral solvers. Particle in Fourier, there are no cells. So here essentially these terms, they are computed by continuous convolution. Okay, so here JK is just the projection in the Fourier space of the current density that you can compute from the particles. And the particle in cell flavor with a DFT, where essentially you replace those continuous convolutions by discrete convolutions on a grid, on a DFT grid. Okay. So there are some advantages here and there, but the main point is that with our Hamiltonian framework, we can analyze these two types of methods in the same set. And we distinguish the two methods here just by the projections, PL, different projections that we use to go from the particle world to these discrete Fourier spaces. And we can also study anti-aliasing techniques, Fourier backfiltering, Fourier smoothing, and so on. So what are these projection operators? What can we take for the projection operators and still having these important commuting properties? We can have first a gridless. For the gridless setting, we can just use L2 projections. Okay, so we defined these projections as L2 projections on the Fourier spaces, and they will commute with the differential operators. It's easy to see that. And we can also define them through a grid by computing, by using discrete Fourier transforms. And in order to have, so this is the discrete Fourier coefficient of J, of a function G. And in order to have this commuting property, so if you use just the DFT projections, they will not commute with the differential operators. If you want them to commute, then you start with this one that you define as a DFT projection, and then you go up in the sequence by taking the DFT of the derivative and by taking the antiderivative in Fourier space, so that you actually commute with the differential. Okay, so it's an ad hoc construction of DFTs that will commute, and this is all well defined and posed. And it allows to study spectral particle in cell schemes in this framework. So it's another example of application of this framework. Okay, and so now I will show you what it looks like to actually derive the variational FEMPIC scheme with this in this framework. So I recall here the continuous Lagrangian functional by law, and we approximate it. So we replace it by a discrete Lagrangian functional that is a functional on the particle velocities, positions, and potentials phi h, ah, and the coupling between the two is represented by these AS and phi s fields, which we decide we take as ansatz these fields. Okay, so these are so this is a coupling field. I should say a coupling potential, vector potential, and a coupling electrostatic potential at a particle position. And we don't just evaluate A at the particle position, we integrate it against the projection of this particle shape function. And here, similarly, for the coupling electrostatic potential, we integrate, we take an L2 scalar product of phi h, which belongs to the V3 discrete space. We take the product against the projection of a smooth particle, of a particle shape. But actually, this S, it may be a Dirac mass. You are allowed for certain projection operators. If the projection operator is well defined for measures, then you are allowed to take a Dirac mass for the shape function, or you can take also a smooth shape function if it's more efficient, if it's better, if you want more smoothing also. And the game then is to use an action principle based on this particular Lagrangian. Okay, so here I show a little bit some of the computations. And so you write the Euler-Lagrange equations, okay, for your discrete functional. So here is one for the variations in the particles. And what do you get? You get something like that. So for this part here, you have essentially the time derivative of the velocity against one in one direction. So E alpha is the unit vector in direction alpha. And okay, and then when you evaluate these functional derivatives, then you have these expressions here that involve these different terms and the coupling terms, so the projections. And here you only play with the commuting projections of the projection operators. So here there is a typo. This should be P2. Okay, when you commute P3 and divergence, you should have P2 here. So it's a good pedagogical example. And okay, and then you gather the terms, and what you have at the end is a term that is essentially the discrete magnetic field taken as a product against this. So this is essentially, you see, V cross B term with the projection here, and this you can think of a Dirac mass centered at the particle position here. And here you have essentially the electric field evaluated at the particle position modulo the smoothing properties of the shape function. Okay, so if you see this as an L2 projection and this as a Dirac mass, this is just the evaluation of the electric field at the particle position, and this is just the evaluation of this magnetic Lorentz force at the particle position. But with general P1 and P2 operators, with general shape functions, you could have something that is smoother and less localized. And so this is the expression of the coupling fields. Okay, they are here. This is the expression of the coupling fields in this general framework. And likewise, you would have an expression of the coupling current density, the discrete current density in this general framework. Okay, so this is the variational system that you get from this derivation. The discrete, the projected field current density is here, and the coupling field is the one that I showed before. So again, I show again this main FEM-peak loop. So now you have an explicit answer for these coupling terms that is derived from a variational principle. And the main result is that this discrete nonlinear system satisfies a Hamiltonian, it has a Hamiltonian structure. So here I recall the Hamiltonian structure of the continuous solutions. And this is the Hamiltonian structure of the discrete solutions. You take an arbitrary functional of the discrete solution, and it satisfies this evolution equation with a discrete Hamiltonian, which is very close, which is very natural here. But we also have the discrete Poisson bracket for functionals of the discrete unknowns, which are here. And you can see that it's completely consistent with the continuous bracket of Morrison, Marder, and Weinstein. You can apply that to spectral solvers. Then you will have these projection operators. Let me see. Maybe I will stop in 5 minutes to allow for a few questions. So okay. So what I can say about that is that here the projection operators, they are still general in the Fourier modes when you compute that with the Fourier modes, and still with the general projection operators, you can write the resulting, so the nonlinear system in Hamiltonian form like that with this Poisson matrix and the functional derivatives of these discrete Hamiltonian. And this to have the Poisson matrix written here explicitly is interesting if you want to do some Poisson splitting or Hamiltonian splitting. So for the time schemes, Hamiltonian splitting consists in writing subsystems, substeps by using subparts of the Hamiltonian, or you could also split the Poisson matrix in different skew-symmetric matrices, and these will give you different time schemes that preserve some invariants. But you can already verify, check by hand that the Gauss laws, which are Casimirs of the Poisson bracket, are preserved with this scheme. The energy is also preserved. The momentum, in general, is not preserved by this approach. Here I write the discrete momentum. And if you do the computations, you will see that the momentum is preserved if the projections are the same component-wise. Okay, if these two projections are vector valued, P0 and P3 they are scalar valued. So here you see in the momentum balance, you have some terms that involve P2, P1 with some components, P3, P2. If you want the balance to be 0, you need to have the same projection operators, and this is typically what happens when you use L2 projections. Okay, when you do L2 projections to couple the sources in the Fourier spaces, then you will have a momentum conservation, and this is what happens with the particle in Fourier schemes. So the particle in Fourier schemes, they are variational, they are Hamiltonian, and they satisfy an exact conservation of momentum. If you use a grid, then you have a discrepancy between the different projection operators, and the momentum will only be preserved approximatively. But the closer you are to L2 projections, the better the conservation of momentum. So you can play with that. You have a degree of freedom here in the discrete projections with a grid if a momentum is particularly important. And I should also mention that there is a momentum preserving variant of the Hamiltonian schemes of the variational schemes. So the general form of the variational FEM-PIC schemes that I described does not preserve momentum in general, but you can redefine, change slightly the coupling field, not the coupling density, but the coupling field in such a way by switching some of the projection operators in particular, but still in this general framework, and to obtain a nonlinear scheme that preserves exactly the Gauss laws and the momentum, if this is what matters for your simulations. And when you have this property, then the two are the same. The two methods coincide. Okay, and I can show a little bit some of the equations for now the fully discrete schemes in the Fourier case in the spectral case. When you split the Hamiltonian with a term that essentially has the so again Hamiltonian splitting means that here you have substeps where you solve this equation, but not with the full Hamiltonian here, just with one part. So for the Vlasov-Maxwell equations here, a particularly interesting, convenient splitting is to take an electromagnetic part of the Hamiltonian, which is this one, and then split this one dimension-wise. So you will have a first. So this matrix here is a diagonal. Is a diagonal matrix. So there is no coupling between the dimensions of the velocities. Okay, so you will have it's the L2 norm of the velocities. Okay, so you will have a first kinetic Hamiltonian part, which will be the kinetic energy in x1, x2, and x3. Okay, and if you do that, you have different steps. So this is the electromagnetic Hamiltonian step. You have trajectories, equations for the trajectories and equations for the fields, and written in terms of the discrete coefficients. Everything is explicit, and the exact solution of our time step is also explicit. There is a full decoupling of the equations, and you have an explicit solution. And the same holds for the kinetic Hamiltonian steps. These are the equations for the substep. And you have an explicit, so these are the time equations in terms of the different all the coefficients. And you have explicit formulas, explicit solutions for these time equations. The resulting scheme, so here will be a spectral particle in cell. Okay, if you use for the projections these commuting DFT projections. So it's a non-standard DFT projections because you take the DFT of the derivative of the source and then you take the antiderivative in Fourier space. And but it is variational and Hamiltonian. Again, you can check the preservation of the different property of the different invariants at the fully discrete level. So at the fully discrete level, the Gauss laws are exactly preserved. And the energy, so the energy is not exactly preserved with Hamiltonian splitting techniques, but it is preserved within bounds. And so it depends on the time step. And if it is preserved within bounds for arbitrarily large times. And the momentum, again, there is a discrepancy in the projections if you want to preserve the momentum. And so you either go to the momentum preserving variant or you don't have a momentum preservation. Okay, and the last thing was that if you use this momentum preserving variant, then you end up with the standard DFT projections of spectral peak. So the standard spectral peak method in this framework can be seen as the momentum preserving variant of the variational FEM-peak scheme with the spectral solvers and these DFT projections. Because at the end, so here you see you have P2 in the equations, but when you integrate in time these equations, the formula for the exact solution will involve the P3 projection, which is not completely obvious here, but you have an interplay between the time derivatives and the gradients and the divergence of the shape functions using again the commuting properties. And so the explicit solution will involve only P3, which is the standard DFT projection. Okay. Okay, and there are some numerical validation, but this is essentially we were using small numbers of particles and playing with the orders of the smoothing or the orders of the solvers. Here it's in Fourier space just to check that all the theoretical bounds were satisfied in practice, that the conservation of momentum here was essentially depending on the time step, on the oversampling, and we were also studying the anti-aliasing properties when you use the shape functions to smooth the source before taking the DFT, and then you back filter to avoid damping too much the modes that are close to the sampling limit. Okay, so we were studying a little bit these issues in this framework, and it works well. And okay, so I conclude here. And so in summary, okay, we have this unifying framework, and I would just essentially like to acknowledge again my co-workers, Jakob, Katharina, Eric, Yaman, and Said. And there are some papers or preprints if you want to see more details. And the next slide, the next talk by Eric will present extensions essentially of these approaches to more complex models. Thank you.
Thank you very much. Thank you very much. I have two questions, both very basic. I'm very basic. The first one is, I don't understand your distinction very much between gridless PIF and DFT.
Yes.
Once you use a computer, eventually that Fourier transform is going to be some kind of discrete Fourier transform.
Yes, because
so how would you do PIF without a DFT in a computer?
Yes, that's a good question. So I think it was here.
Yes.
Yes.
Right. Those operations on the left in practice, they end up being DFTs. No, something like that.
You can think of the case where so J was it's the current density just carried by the particles. So if you take a Dirac mass here,
okay,
you put it in the integral, in the continuous integral, and you will just evaluate essentially this exponential, this complex exponential at the particle position. Whereas here you first evaluate the current density on a grid. So dx is the DFT grid resolution step, and you take a DFT or an FFT of that discrete current density that is evaluated on the grid. So you first difference is that this one is well posed with a Dirac particle. It may be yes, and this one not. Here you really need a smoothing. Another important difference is that when you take the L2 projection of some current density, you compute the exact Fourier modes of the current density, whereas here you will have aliasing because of the grid. So you will have the folding of the upper part of the spectrum.
Yeah, so basically for the one on the left, you're hoping that you have a representation where you can do those operations by hand, really. Representation for JN and EH.
Yes, well, so here, if you have point particles, then you just evaluate.
For sure, yeah.
Yeah, so it's very simple. It's also expensive because then all the particles will talk to all the Fourier modes. We'll have so this is expensive. So here it's also the case, but here you have an FFT, which is very efficient to compute that. And another problem. Okay, so here if you have a smooth shape function, then you can take it out of the integral, and you will have the Fourier coefficient of the shape function. So you will have the direct filtering in Fourier space thanks to the shape function.
Thanks a lot. And my second question is, have you groups start to think about particle in Chebyshev or particle in Lejeune for non-periodic problems?
Yes, so I know that Jacob, during his PhD, has studied that. So, as Eric would say, it's written in Jacob's PhD.
Thank you.
No, yeah. I think he was quite happy with the results. Yeah. There is one question in the chat, but I don't know.
That was me asking about the pair.
Okay.
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 Thank you again.
Thank you.